So we're done with part A. Now let's move on to part B, which is timing service. Timing service requires timer, and timer is interrupt driven. So we're going to discuss interrupt handling. In real-time operating system, interrupt handling must be fast. That basically means that we want like a short latency to respond to interrupt, and we want fast processing by interrupt handler. And interrupts may also cause a change in the state for some blocked processes. For example, if a process is blocked for external event to occur, it will have its state change to ready and be placed on the ready process queue due to certain event occurs. And this event may be caused by this interrupt. One possible interpretation of an interrupt is a hardware message that requires a short latency and quick service. And then the design issues we need to consider are the following. First, does the interrupt handling code run as part of a kernel within a process? And if yes, which process? Second, are interrupt handlers themselves interruptible? That is, do we support nested interrupt handling? And the third is, if OS is preemptive, it needs to deal with the possibility that an interrupt results in a higher priority process becoming ready. Hence, when we return from the interrupt, we may not return to the interrupted process. So let's take a look at the interrupt handling sequence. So a process is executing, an interrupt happens, and then we enter the interrupt handler. Upon entry, we save the context of the current running process, and then we service the device. Then after that, we update any state change to a process. Remember, the interrupt may cause certain processes becoming ready. So this step is very important. Then we go to exit. So when we exit, we check the ready queue for a ready process of higher priority than the current. If there's a process that becomes ready and that has higher priority than the current process, which is the interrupted process, then we put the current process on ready queue. Then we dequeue the selected new process, and we restore the context of the new process to match the pre-interrupt state. Then we return from the interrupt handler. So when we return, possibly we're not in the same process. We can see the interrupt handler must interact with OS processes. So the design we're taking in this lab is to create a special process called I process or interrupt process, which gets the CPU from an interrupt handling sequence, not through the scheduler. And it never blocks. If it invokes a kernel primitive, then that basically means if I have a blocking version of kernel primitive, I need to create a non-blocking version of it as well. And the interrupt handler will call the non-blocking version. The interrupt handler routine starts the appropriate I process. So conceptually, this I process has the highest priority, and it is scheduled by the interrupt, and we do not handle nested interrupt. So this interrupt process has a special state transition. It is either waiting for interrupt or it is executing. And whenever it always runs from the very beginning to the end without being interrupted again. So we can have a PCB that is associated with the I process, and we can give it a special state called IPROC, and like permanently. And it's always ready to run, but it is not on any ready queue. So this I process is a very special. When we are in I process, we are already in handler mode. That basically means we can only call the kernel primitives. So any kernel primitives can make a function call. However, we do not allow I process to be blocked. What's the consequence of blocking an I process? We're going to get blocked forever. We will never be able to continue the execution. Well, then the other thing is because we cannot be blocked, so any kernel primitives that can block, you need a non-blocking version of it. That is, instead of blocking, then you return a null. For example, the synchronous receive message primitive, right? It is a blocking version. Then if there's no message and the I process calls the receive message, what's going to happen to I process is going to get a null pointer. And similar to other primitive. So I would like you to think what's the other blocking version of primitive you have and how you should change it. Let's take a look at one example implementation of the timer I process. The timer I process enters through the timer IRQ. Here we use timer 0, and we immediately turn off the interrupts because we don't handle nested interrupts. The first thing we do is to save the context of the current process, and this is done in assembly code. And then we're going to switch to the I process as our current running process. And we load the I process's context when we do this switch. Then we call the timer I process C function. So the main logic of the I process is implemented in C. And this function is not interruptible. It runs from the very beginning to the end. And once the I process finishes its work, it's going to call the scheduler to pick next ready to run process. And this process could be the original interrupted user process, or it could be another new process that just becomes ready because of this timer interrupt. And then we restore the context of this newly picked process. We turn back on the interrupt, then we return. Again, this piece of code usually is done in embedded assembly. And I have the starter code context switching IRQ project on GitHub to show you one implementation of this I process by using embedded assembly code. Okay, so now let's talk about the timing service design of a real-time operating system. This is a very fundamental issue. It involves two parts. The first part is interface protocol design, and the other one is internal design. For our particular lab project, we provide very basic service only, and it is a timeout mechanism. There's no cancellation. Basically means there's no way for us to cancel that particular timing service once we have filed the request. And our service request is based on expiration notification by messages, like the delay send, which we are going to talk about more. And the internal design, the timing service basically is implemented by the I process. And for the service request, a user process sends a request message to the timing I process by using the delay send API. And then for the timeout notification, the I process basically sends the message back to the destination. So the I process is like a middle person that relays the message at the right time. In this lab project, the API for the user process to request a timing service is delay send. And it takes 3 input parameters. These two are straightforward. And this one is the delay in milliseconds. What happens is whenever a user process calls delay send, it will specify a receiver ID, but actually this message will first get routed to the timer I process. So timer I process receives this message with a timeout value. And remember we have the message envelope header structure, and we have a placeholder. Well, in that placeholder where you can put 20 bytes, you may want to put the timer I process PID there so that you know this is a delay send message and this is the real destination receiver like PID. And you may want to put the number of clock ticks instead of number of milliseconds in this field, because converting it to a number of clock ticks is easier on the OS side. Well, having said that, we configured our starter code so that every 1 millisecond it's 1 clock tick. So for us, the delay is in the same unit as the number of clock ticks. So you put out this information and other variables if you want to keep track of more information. And this is your message. And then every timer interrupt, this number of clock ticks gets decremented by 1. So once this number of clock ticks, this is like a timeout value, reaches 0, then timer I process will send this message over to the receiver. So we need a timeout queue in order to queue up all these timing requests, and we need to sort them by the expiry. So here again, we have a queue. And if you have generic queue data structure, it is very easy for you to do this part. In the previous slide, we talked about saving the expiration time in number of clock ticks, and every timer interrupt, we have to decrement that timeout value by 1 clock tick. If we have many messages queued up in the I process, that basically means for every message, we have to do this decrement operation, and that's quite a lot. And we want our timer interrupt service routine to be fast. So to reduce the CPU overhead, one strategy we could do is to replace the expiry time by the number of clock ticks after the expiry of the predecessor in the list. So we use relative expiration time in the list. So I'm going to use an example to illustrate the idea. Imagine I have 4 delay send messages, and there are 25 clock ticks, 55 clock ticks, 2 messages, and 65 clock ticks. So when I create this list, I will use 25 as the head of the queue because that's the smallest timeout value. But for the 55 clock ticks, I use the relative timeout value relative to 25. So that basically means 25 plus 30, that's 55. I have another 55 clock ticks, and 55 relative to 55, it's 0 difference. So I put 0 here, that's 25 plus 30 plus 0, that's another 55 clock ticks. And then finally, 65 relative to 55, that's 10 clock ticks. So 25 plus 30 plus 0 plus 10, that's 65. When I have this list, every timer interrupt, I only need to update the head of the queue. So I decrement this by 1, that everybody in the list timeout value, their absolute timeout value gets decremented by 1. So at every clock tick or timer interrupt, the timer I process increment the current time, basically means decrement the timeout list, and then cause receive message repeatedly to retrieve any new requests, and very important, it needs to call the non-blocking version of the receive message. So you need to come up with a non-blocking version of receive message inside the kernel, and let the timer I process to call that particular version of receive message. And why do we need to do this? Because from the previous timer interrupt to the current timer interrupt, in between there was like 1 millisecond passed, and maybe there were a couple of delay send messages got sent by the processes. So we need to service all these messages. If there are new requests, then it adds them to the queue, the timeout queue, and then we basically check if any timing requests have expired, and if yes, then we send the messages to the destinations. Here's the pseudocode of the timer I process. First, we need to update the timeout value in the queue, and then we need to service any pending requests and add them into the timeout queue. Then finally, we'll check the timeout queue to see whether there are any messages that have reached the timeout value. If yes, then we will dequeue them and send them over to the destinations. So in most of our slides, when we present the pseudocode, we mentioned the pseudocode was for a non-preemptive kernel. So how do we change it to a preemptive kernel? Actually, it is very straightforward. You follow exactly the same logic as you did for the release memory block in P1. So all you need to do is on return from send or any primitives that may make another process ready, we check if the highest priority ready process's priority is greater than the current running process's priority. If yes, then we do preemption. Now the question is, what if the current process is an I process? Well, I process implicitly has the highest priority, so it cannot be preempted. That basically means when I process finishes its job, when we are ready to return from the interrupt, then we check whether the priority of an interrupted process is still the highest. If not, then we context switch to the higher priority ready process. We've already seen these slides a couple of times. In part B, the most important thing is during kernel initialization phase, we need to initialize timer interrupt. And for the process control data structure, we need to add the timer I process initialization. For submission, we're going to use Git again, and remember to tag your commit with P2 P2B-submit. So that's it. That's P2 tutorial, and thank you for watching.